So for our last example, we're going to find the general solution of y double prime minus 8y prime plus 20y is equal to 0. So as usual, when you have constant coefficients, we're going to set up the characteristic equation, r squared minus 8r plus 20 is equal to 0. So it's the same equation as the differential equation, except we've changed the y's to r's, and we've changed the derivatives to exponents. And now we would try to factor this, but it turns out it doesn't factor. So instead we're going to go to the quadratic formula. So we get r is equal to negative b is positive 8 plus or minus b squared is negative 8 squared, so 64 minus 4ac, a is 1, c is 20, all over 2a, so that's 2. Now 4 times 20 is 80, so we get 64 minus 80 there. 8 plus or minus 64 minus 80 is negative 16, so we get a negative 16 under the radical over 2. Now the square root of negative 16 is imaginary. That's 8 plus or minus 4i over 2. And that simplifies down to 4 plus or minus 2i. So as usual, the complex roots come in conjugate pairs. The 4 is my alpha, the 2 is my beta, and I'm going to drop the alpha and beta back into the generic form for the general solution that we had back at the beginning of the lecture. So my general solution is C1 e to the alpha t, alpha is 4, times cosine of beta t, beta is 2, plus C2 e to the alpha t times sine of beta t. And since I don't have any initial conditions on this one, I'm going to stop there and just say my general solution is the last word for this example. So to highlight what we did there, we took the original differential equation, translated it into the characteristic equation, which didn't factor nicely, so we went to the quadratic formula to solve for that. So we ran it through the quadratic formula. Turned out we got 4 plus or minus 2i, so that gives me my alpha and beta that I can plug back into the generic form for the general solution. So there's alpha, there's beta, there's alpha, there's beta. It's always this form, the e to the alpha t cosine beta t, e to the alpha t sine beta t, and then you tack constants on each one. So at this point we have no initial conditions, so we're done with this example. If we'd been given initial conditions, we would have used them to figure out what the constants are. We would have gotten a couple of equations and a couple of unknowns. We don't have that, so at this point we're done with this example with the general solution. So that's the end of our lecture on complex roots to the characteristic equation when you have second order equations. We'll move on in a later lecture and study what happens when you have multiple roots, when you have repeated roots to the characteristic equation. So that'll be the next in our series of lectures on differential equations. You're watching Educator.com, and my name's Will Murray. Thanks for joining us.